Relation between current density and drift velocity. Consider a cylindrical conductor having n electrons in the cylindrical volume P-P. If these electrons cross the cross section in time delta t with drift speed Vd, then Vd into delta t equals to L, here L, or A into Vdt equals to A into L. So number of electrons per unit volume is n equals to n by La, called number density, or n equals to n by A into Vd into delta t, since from 1 L is equal to A Vd. So hence n, total number of electrons will be Na into Vd into delta t. Now charge crossing the cross section in time delta t is delta q given by Ne equals to Na into Vd into delta t into E, or Ne Vd delta t into A, question 4. But from the definition of current I equal to delta q by delta t, E N A Vd delta t by delta t, or Ne A Vd, or I by A equals to Ne Vd, which is equal to J, or J equal to Ne Vd. Again, putting the value of Vd in equation 5, we have J equal to Ne into Vd, Ne into E by M into tau, or Ne square tau E by M, or J equal to Ne square tau E by M. Equation 4. Where Ne square tau by M is sigma, is the conductivity of materials. So hence J equal to sigma E, equation 5, or J equal to 1 by rho into E. In vector form, J vector is equal to sigma into A vector. Also E equal to rho into J vector, or E vector equal to rho into J vector. Again, sigma equal to 1 by rho. This implies rho equal to 1 by sigma equal to 1 by Ne square tau by M. Hence rho equal to M by Ne square tau, or rho equal to M by Ne square tau. Now dependence of resistivity on temperature. Metals or conductor. For metals, resistivity is given as rho equal to M by Ne square tau, or rho proportional to 1 by N into tau. M and E is constant here, as N number density, that is electron number density, and does not change with temperature. So rho depends only on tau, that is rho proportional to 1 by tau. Now with increase of temperature of the conductor, the collision between electrons and ions increases due to increased vibration of ions, resulting into decrease in relaxation time tau. Thus the resistivity rho proportional to 1 by tau increases with temperature, because tau is decreasing, so rho will increase. Second, in semiconductor or insulator, the variation of resistivity of a semiconductor or insulator with temperature is given by rho equal to rho naught e to the power E by 2 kT, where E is the energy gap between conduction band and the valence band, and K is a Boltzmann constant. T is the absolute temperature of semiconductor. So with increase of temperature, resistivity decreases. Energy gap E for insulator is much more than that of semiconductor. A current of 1.0 ampere exists in a copper wire of cross section 1 millimeter square. Assuming one free electron per atom, calculate the drift speed of the free electrons in the wire. The density of copper is 9000 kg per meter cube. According to mole concept, 1 mole equal to n by Na equal to m by m. That is number of electron, number of atom divided by Avogadro number, or given mass divided by molecular mass, and this equals to n equals to m into Na by m, where m is the given mass of element, where m is the given mass of element, and m is the atomic mass of element, n is the number of atoms in a given mass, and n is the Avogadro number 6.023 into 10 to the power 23. Now J equal to Ne Vd, so Vd equal to J by Ne, or equals to I by A into Ne. Hence Vd equals to I by A, and N is equal to N by V into E, or equals to I by A, putting the value of N, M Na by M into E by V, or I into M, A into M by V, Na into E, and Ma by V is the rho density of conductor. So I Ma Na into A rho E. Here it is to keep in mind that this is the not resistivity, it is density of material, because we have taken mass by volume. So this is the density. Rho here represent density. Now we have Vd equals to, given current is 1 ampere I, and Avogadro number, molecular mass of copper is 63.5 into 10 to the power minus 3, and Na is 1 into 10 to the power minus 6 into 6.23 into 10 to the power 23, 9 into 10 to the power 3, 1.6 into 10 to the power minus 19. Putting all the value we have, solving, and the final value 0.0707 millimeter per second.